So in our last three videos in this section, we are learning about Newton's laws. First of all, his three laws of motion: inertia, forces, and action-reaction pairs. And then we had a video that let us make free body diagrams. How do we work with these forces, and how do these forces contribute to creating an acceleration on some object? Then in our last video we said, well, what are some new forces that we could apply? Force of friction was the example that we looked at. But Newton's second law, net force is equal to mass times acceleration, has two sides on it. One of the sides, yes, is looking at forces, but the other side has accelerations. And what happens if we're in some scenario where we have some acceleration that's coded into the problem already? Maybe I'm in a car that's accelerating. Maybe I'm in an elevator that's accelerating. What if I'm on some amusement ride of some kind that is accelerating? How am I going to see these systems evolve? And this is the last of our topics this term. How do we look at Newton's laws when we are in an accelerating reference frame? And the two scenarios that you look at are most often going to be associated with an elevator or with some sort of moving in some circular motion. So there's a page in the notes where I talk about these different kinds of things. If I'm in an elevator, I'm in this closed box, I can't see outside the elevator, I don't know what's going on, somebody hits a button, and all of a sudden I feel myself jammed against the floor. There was no string attached to me. There was no individual person that was pushing me one way or another, but I felt this influence nonetheless. It really felt like I was getting pushed down. But was I getting pushed down? Not really. What happened is the elevator is accelerating around you. Similarly, if the elevator is going down, I feel myself, whoop, I start to float a little bit before it normalizes back down again. Was there some string that was pulling me up? Was there some weird person that was lifting me? No. What happened is I'm seeing the world through some accelerating reference frames. And so because of that, some things don't make sense. And maybe some of you aren't comfortable in an elevator. I had an uncle that does not like being in enclosed spaces. He does not like being in elevators. But he certainly is in cars that might end up going around in a circle. Or maybe we have some mass on the end of a string that we have as a child's toy or something like that, and we're spinning it around. We saw in our last unit on kinematics that in order for that thing to go in a circle, whether it's your car, or whether it's this mass on the end of a string or whatever, in order for it to go in the circle, it has to accelerate. What direction is the acceleration? It has to be centripetal. It has to be center-seeking acceleration. So that being said, each of these scenarios is a scenario of an accelerating reference frame. In these scenarios, what we do is not alter the forces on the left-hand side of Newton's second law. We alter the accelerations on the right-hand side of Newton's second law. So putting all of that together. Now that being said, let's say we wanted to look at this scenario, and particularly we're going to relate this to, there's lots of things that we could look at, elevators and the like. And I have examples of these things that are already in the Canvas shell. But I want to focus primarily on what it means to have centripetal acceleration. Because like I said, intuitively, this isn't what we feel. Like I said, we're driving around with our friend, we're sitting in the passenger seat, your friend jerks the wheel in one way or another, and you get slammed up against the opposite door. It sure doesn't feel like a center-seeking acceleration to me. It feels like I get jammed to the outside door. So what I sort of felt was a centrifugal, center-fleeing force. But that's not real. If you were to look at the problem from above in a non-accelerating reference frame, and the car starts to turn, what you would see is Newton's first law taking hold. Your body trying to continue on doing what it was doing before. But because the car is turning around you, you trying to move in a straight line puts you on the outside door. It felt like a force to you. It feels like getting jammed up against that door. But it turns out for you to be in the passenger seat going around the circle with your friend in the car, that door has to be putting a centripetal force on you. Otherwise, you go in a straight line out the window. Something you don't want to happen. So there really is a centripetal force on you, making you go around the circle. That force is being applied to you by the door, the center-seeking force. You are putting a centrifugal force on the car, a centrifugal force on the door. You're pushing outwards on that, center fleeing as a force. But this centrifugal force is something that's commonly called a fictitious force because it's not a real force, at least not a real force on you. It's coming about because of sitting in an accelerating reference frame. This would have never happened. We never would have had this confusion if we hadn't been in a frame of reference that was accelerating. If we're sitting in a car that's trying to turn, we're in an accelerating reference frame. We are not a good judge of Newton's laws in that scenario. Similarly, if we're on an elevator going up, elevator's going down. If that elevator is accelerating, we might feel weird things. We are not good judges of Newton's laws when we are in such a reference frame, an accelerating reference frame. We have to be in a non-inertial, or we have to be in an inertial reference frame for things to hold. Non-accelerating, that's the kind of thing that we need. Now, one of the common scenarios that we most often look at when dealing with these phenomena is looking at centripetal acceleration. How do we make things go around a circle or make things go around a curve? Now, I happen to have grown up in Nebraska, so this is not a road designed for Northeast winter, but it could be a road designed for Northeast winter, just like it's a road designed for Nebraska winter. Because at the end of the day in winter, ice can show up on the roads. Friction can go away. And so how do we make a car go around a corner when we don't have friction to help us? Well, what we could do is bank the road. If we bank the road, the banking of the road, the normal force that's applied by that road will lead to some new centripetal, center-seeking acceleration for us. So here is a cross-section of some car trying to navigate some turn. The car is moving away from us, but we're on a banked road, and the banking of this road has some angle theta. The normal force is along the perpendicular, just like always. The weight of the car is straight down, just like always. But it turns out that if the car is safely navigating this turn, it's not going up the ramp and it's not going down the ramp. It stays at the exact same height. So there's no acceleration up and down, but in order to navigate the curve, it has to have a center-seeking acceleration. We will have acceleration in the negative x direction here. As far as direction is concerned, magnitude has to have some x component, but it doesn't have any y component. So if I was to take this free body diagram of the car, up and down we've got an n cosine theta minus mg, but I don't want the car to accelerate up and down. The center-seeking force is n sine theta, and this center-seeking force has to lead to center-seeking acceleration. We remember from lecture 2D that the magnitude of this center-seeking acceleration is v squared over r. Okay, well now with this information, I could do a little bit of solving to figure out what angle would be needed for a car to navigate a turn safely when there's no friction. So from the first equation, we can get an expression for the normal force. We plug that normal force into the second equation. That's what's going on right here. Turns out that sine theta over cosine theta is tangent of theta. Divide both sides by mg. We get a v squared over rg. And so the angle that is required to safely navigate a curve in the absence of friction is the inverse tangent of v squared over rg. Okay, so a couple of things here. If my velocity goes up and up and up, it turns out that I'm going to need better banking. If the radius goes down, I'm going to need bigger banking. But let's just say we threw out a couple of numbers. Maybe for a typical car driving in the winter, they might be traveling at about 60 miles an hour, which is 30 miles per second. Similarly, the curve that you're trying to navigate and go around maybe has a radius of 1/4 of a mile, give or take. So this is a nice gentle road. The radius then is about 1/2 kilometer. Putting these numbers in, taking the inverse tangent, we find out that a slope or a bank is required of about 10 degrees. That doesn't sound like much, but 10 degrees of slope is a lot of slope. It's hard to walk on. So this is bigger than is actually in practice, but maybe it's something that's tangible that could be done. Now, using this exact same expression, we could look at the case of NASCAR. Why doesn't NASCAR run on ice? Well, NASCARs are running at about 200 miles an hour, which is about 100 meters per second. They're going around maybe 1/8 of a mile turn at the end of the track, which is about 1/4 of a kilometer. The banking that would be required is 76 degrees. 76 degrees is pretty steep banking. That's not what you see at Bristol. That's not what you see at Daytona. This is very, very different. And this is why NASCAR doesn't run on ice. They very, very strongly need friction, a frictional relationship between the tires and the road. It's important. Banking alone is not going to do it. But the key part of this example was we were using a component of the normal force to make some new acceleration. This isn't how we talked about acceleration in the last 3 videos associated with Unit 3 here. Now what we're saying is, okay, I have all these forces, and I know how to deal with those forces. How do I use those forces to make this special kind of acceleration that I happen to know? And if you were to go through the examples in Canvas, there's lots of different ones. We can do things on elevators. There's videos associated with watching what the physics of NASCAR is associated with this. We have roller coasters going around. But I want to look at one quick problem before we close up on this lecture. I'm going to look at the case of some little nugget on the end of a string. So here is some pull. On some pull, I have some little mass. So the force here is mg. But this little nugget is held in place with some string tied to the top. This string has some tension, T. Are there any other forces that are working on this little nugget? No. But what I would like to figure out is if this string is a length L long, and I would like the radius of circulation for this little nugget to be R, how fast does this thing need to be spinning around the circle? What does its speed need to be as it moves around the circle? So again, if this mass has a circular path of radius r, what tangential speed v is needed as it goes around the circle? So looking at this, I don't want the mass to be going up and down along the pole, but I do need to have some center-seeking acceleration. So looking at the free body diagram here, maybe we have this theta and this theta, and what we see is that the force up, t cosine theta, and the force down, mg, are forces up and down that must sum to 0, because I don't want acceleration up and down. But if I was to go right and left, there's a center-seeking force, t sine theta, and it has to create a center-seeking acceleration, v squared over r. Right? Now, in this problem, the one here on the right in particular, I need to find out what this velocity is. But I don't know the tension. I get the tension from this part of the problem. So again, I have two equations, and I have two unknowns, t and v, and t. So over here, I see that t is mg over cosine theta. And I can take this and plug in over here. T, which is mg over cosine theta times sine theta, is equal to mv squared over r. Sine theta over cosine theta is tangent theta. Is equal to mv squared over r. M cancels out on both sides. Tangent of theta is equal to v squared over rg. We've seen this before. This is exactly what we saw with this center-seeking force in the past. But, now I'd kind of like to look at some of this thing, because we weren't told what the angle theta was, right? We were told L. We were told R. So looking at using a little bit of trigonometry, what we find is this distance is L squared minus R squared. So in this expression, tangent of theta is actually R opposite over adjacent L squared minus R squared, and this is equal to V squared over RG. Interesting. So if I was to solve this for the velocity that is needed for it to go around in a particular circle, the velocity is going to be g r squared like this, and so the velocity is actually g r squared L squared minus R squared to the 1/2 power. This is the velocity that is required. Now, this looks kind of weird. I'm taking square roots of square roots. This seems needlessly complicated. But let's take a quick analysis to see if anything from this makes sense. For example, what if we wanted this radius here to be 0? So the nugget is sitting right next to the rod. If I set r equal to 0 here, r equal to 0 here, the velocity needed for that to happen is 0. I don't have to be making it move if I want this radius to be equal to 0. Now, what if I wanted this radius to be L? Now, in this expression, r squared becomes L squared, but down here, this becomes a 0 in the denominator. It takes infinite velocity for that radius to actually be L. More manageable velocities if r is some fraction of L. Maybe it's half L, or a third L, or 2/3 L. Those are all totally fine. But to actually get r up to L would take an infinite amount of speed, something that clearly doesn't happen. So even though we don't have any numbers in this expression, it turns out with the things that were given to us, in this case r, L, and mass, we could do all this. In fact, what we find is that mass doesn't matter. We could have a marble, we could have a bowling ball, whatever. If we want this particular radius on a string of this particular length on some pole, this is the speed tangentially going around the circle that's going to be needed from that. Now, like I said, if you're following along in Canvas, there are a lot of additional examples of using centripetal acceleration and forces that lead to those centripetal acceleration. These are centripetal forces. There are some examples of physics on an elevator, so to speak. So I encourage you to look at those things. But this is the topic of how we can alter not just the forces in Newton's second law, but we can also alter what it means to have accelerations in these problems. And if there is some acceleration due to our weird reference frame, we can still do some calculations and we can still solve some things related to centripetal acceleration, centripetal forces.